here. So, thank you all for coming to this ITC Colloquium at a special time. We're very lucky today to have Mark Voit visiting. So, like a few people in this room, Mark got his undergraduate degree at Princeton, then his PhD at the University of Colorado. He then went on to a postdoc at Caltech and was a Hubble Fellow at Johns Hopkins before moving to Space Telescope for a number of years, before finally ending up at Michigan State. And as we heard at lunch today, he is apparently not looking for a job at the moment. So Mark is an expert on galaxy clusters and the interesting physics of the baryons in them, which he will tell us about now.
All right. So, thank you. This picture should be familiar to many of you, partly because a lot of you work on this, and probably because they showed it 3 hours ago on the Twitter. This is NGC 1275, the Central Galaxy, the Perseus cluster, and it has long been well known to be weird. What you see in this picture, aside from the optic light from the stars, are these H-alpha filaments that extend over tens of kiloparsecs. And you see streamers that look like star formation, almost beads on a string in blue star clusters. And if you could see molecular gas, you'd see a bunch of that too. If I can find my pointer here. If you can see the X-ray gas, all this is embedded in hot X-ray medium. Okay? Something that is well studied here by the Chandra X-ray Observatory. And the points I want to make during this talk are, first of all, what we learned from studying galaxy clusters is that the star-forming properties of what's down in the galaxy depend critically on the state of the circumgalactic gas. And since we know that because of the opportunity to see it here when it glows in X-rays, and what we can learn from studying the relationship between the hot gas and the stars that are forming inside of it may have very broad applications to understanding star formation galaxies at all scales where you can't see all this happening. I'm going to argue that the idea that you have gas condensing out of the hot medium turns out to be very tightly linked to feedback. And so much so that the cool gas you see around this galaxy is really an emergent property of the whole phenomenon of feedback. And that can greatly simplify our understanding of how AGN feedback works. Because I'll also argue that it's a very natural regulation mechanism governing how star formation happens in galaxies. So I've been quoting a lot of words today. Cinecosmology. Well, I imagine there's people who have worked on the Western simulation. And I've shown this movie a number of times. It's beautiful. I sometimes speculate we could go to the multiplex and sell tickets, and people would pay to see this movie. And it's an example of movies that have a great deal of influence in our way of thinking about what goes on in space. And sometimes too much so. I don't want to criticize this too much. It's an incredible achievement to make simulations like this. We learn a great deal from them. But sometimes the conclusions we draw from what we see are not as physically grounded as we'd like. It's partly the influence of pretty pictures. And if we wait a few more, maybe another gig year or two, there we go. What we see now is a map of the hot gas. So the gas temperature here, red's hot, blue's cold. And what we see are the AGNs going off and causing what look like big explosions. And in Lustrous, the feedback is notoriously explosive because that's the way the algorithm is set up. And I'm going to argue that a more subtle understanding of how feedback works leads to a less explosive picture for AGN feedback and something that's quite a bit more tightly regulated than you would guess from watching a movie like this. So I threw in this slide a few minutes ago. I went on a run this morning. I've been a runner for a long time. Is that you? Yeah, yes, it is. This is from 1982. I ran by the track, the indoor track, which was brand new, and I ran on it the very first year. I did include the picture at Princeton. I gave this talk at Princeton like a month ago, and I had a picture of me being a guy from Harvard. And I pledged to use that one. And so if you want to understand like how a runner runs, I would say that there's two approaches. One is you can build like something that's like a runner and put lots of wires in it and chips and whatever, and then you can see if the robot runs. Or you can take more of a stick figure approach. And the idea here is what we're really after in trying to understand feedback is understand an emergent property of a complex system. And sometimes when you're trying to understand the emergent property, it's not even germane to think about all the bells and whistles. You don't want to keep tinkering with all the bells and whistles and see if it works right. Sometimes your focus should be more on the generalities of how the system operates, the feedback loops. Because when we think about complex systems, the emergent properties that they have are really due to the feedback loops and govern how they work. And so that's kind of going to be a theme. In a way, I feel completely inadequate when I look at a lecture saying, well, I could never do that. But there are other ways of thinking about things that can give you physical insight in a way that a simulation can't. In order to set this up, I need to go back to basics. If you were sitting down to write a textbook, say 20, 25 years ago, you might have included a galaxy diagram that looks like this. And then you would realize, you know, actually central black holes are pretty important. And so I think over the last 20 years, we've come to appreciate that the central black hole is a component of a galaxy that's as important as all these other things. But now, sitting down to revise the textbook, it's the circumgalactic medium that really has to enter the picture. Because we now know from absorption line studies that most of the galaxy's baryons are out there, most of the metals are out there. And so if you want to understand how a galaxy lives its life, knowing how it's connected with the circumgalactic medium becomes a very important piece of the picture. And it's been undervalued because it's just so hard to see. But I think this is an increasing trend in galaxy evolution studies that you really have to know how the galaxy is collected in the circumgalactic medium to know why it evolves in the way it does. Let's see. Right, so we're familiar with seeing pictures like this of radio jets. This is a non-star forming central galaxy. And just from the morphology of radio jets, you can tell they must be running into something. And that's some sort of circumgalactic medium out there. And the curious thing is, a lot of people think now that the reason this galaxy isn't forming stars is because the black hole has somehow got itself tuned to balance the radiative losses from the circumgalactic medium, which is a puzzle because the black hole zone of influence is down at parsec scales, and it has to balance this volume that's 10 kiloparsecs or more in radius. And how that tuning comes about has been a pretty resistant problem to solve. What helps is seeing the circumgalactic medium. Okay, and so with an X-ray telescope, you can see that, and that's going to be key to trying to solve this puzzle. When I think of cooling, increasingly I think of it in the dimension of pressure and entropy, where entropy in this context is the constant proportionality between pressure and density in this adiabatic equation state. And so you can write down cooling times the function of pressure and density and temperature, or equivalently pressure and entropy, where entropy I will define as kT divided by density, electron density minus 2/3, well, divided by density 2/3 power. And when you do that, you end up with a diagram like this. And the horizontal dimension is the dimension of hydrodynamics, right? Unless you're creating shocks, the pressure is going to move things around in that direction, but those processes are going to be adiabatic. And the vertical dimension is the thermodynamics dimension. And so that's why it's often more useful to use this pair of thermodynamic variables than the pair temperature and density. Let's see, so one of the things I wanted you to notice about this diagram is that in the temperature range that is characteristic of circumgalactic medium, when you change the pressure of the gas, you don't change its cooling time much. Okay? So if you're just pushing it around adiabatically, the cooling time isn't changing very much. Okay? It goes for whether it's expanding or contracting. So the cooling time is really closely linked to the entropy the specific entropy the gas has. If you add heat energy to it, you'll raise its cooling time. If you let heat energy go out, you'll lower it. And what that means is if you want to get higher in entropy and cooling time, often what's necessary is shocks. So in this diagram, shocks will send you this way. And in this temperature range, there's no such thing as shock-induced cooling, right? If you shock it, you're going up in entropy and going to longer cooling time. The way you get back down, well, you can do that with a cooling flow, but in isothermal potential, as you radiate energy, compression tends to keep you at the same temperature. And so in this kind of diagram, the processes of shock heating and kind of radiative cooling flows send you in these directions on the diagram. Now, in 1956, Lyman Spitzer published a really remarkable paper. And what he had available to him were interstellar absorption lines that indicated the densities and essentially the pressures of some clouds that were outside of the galactic plane. The data on which this paper based weren't published for 5 years after he heard about them by visiting William Wunsch at Carnegie Observatories. But he wrote this paper saying, if I know the pressure of these clouds, and I infer a confining medium, and I assume the confining medium is in hydrostatic equilibrium at the virial temperature of the Milky Way, which you infer from the rotation curve, you can get the cooling time of this gas. And it turns out to be 10 to the 9 years. And in 1956, he said, wow, if there's a circumgalactic medium, he called it the galactic corona, then it can cool in principle and fuel star formation in the galaxy, and it can only persist if it's heated. In other words, he had the same conversation we're having in 2017 based on this little bit of data you were able to get in 1956. I think that's pretty remarkable. So yeah, the problem of origin of such a corona reduces primarily the problem of heating, and we're still working on it. So if you take a more modern model of the Milky Way's circumgalactic medium, this is from Chandra data compiled by Miller and Bregman, where they're looking at oxygen 7 emission lines and trying to model the density fall off as a function of radius. You get a cooling time structure that looks something like this. If you do, that's not the Milky Way, that picture up there. NASA has not yet funded a satellite to get us an external picture of the Milky Way. All right, so here now is NGC 4472. Now if you do the same thing for NGC 4472, now using X-ray observations, to say what's the cooling time at every radius? Well, everything's at higher pressure, but the cooling time at each radius is pretty similar. Okay. And this galaxy isn't forming stars. If you then go to M87, do the same thing. Well, you have a lower cooling time out of 100 kiloparsecs, but at 10 kiloparsecs, it still stays around 10 to 9 years. And if you go to NGC 1275, even though the pressures are several orders of magnitude different here, the cooling time at 10 kiloparsecs tends to be of order a gigayear. And something's suspending it there. Okay. So the takeaway from this is movies sometimes gives the impression that quenching is something happens when an AGN blows a galaxy up. Just ejects all the gas from it, and then you're quenched. But the slide I just showed indicates in a lot of these galaxies that are quenched, the cooling time inside of 10 kiloparsecs is like less than a gigayear. At 1 kiloparsec is less than 100 million years. Down inside of that, it's a few tens of millions of years. And so that has to be kept heated in a steady state. And you need to know what that steady state is if you're going to understand quenching. All right, so thermal instability and condensation. Here's kind of the central idea of the talk. I'm going to be showing a bunch of evidence that suggests that the feedback loop involves the transition to a multiphase medium. And so what it hinges on is the idea that the presence of cold gas greatly increases the black hole accretion rate. And I'm not going to bother trying to explain how all that gas gets down to the center. I'm making the point that if you just have hot gas, you can calculate a Bondi accretion rate. It's like the maximum rate at which gas can flow onto the black hole. And if you make the gas quite a bit colder or lower entropy, that limiting rate is orders of magnitude higher. So by condensing gas, you greatly increase the maximum fueling rate the black hole can have. And that very property, if in some general way the process of condensation greatly amplifies feedback, then you'll tend to get hung up at the edge. It's like a transition edge sensor. As soon as you start getting cold gas and ramping up the feedback, that's going to add heat to the system that prevents more cold gas from forming. And so you should be stuck right around the threshold. And this, if it is what happens in nature, greatly simplifies the whole concept of what AGN feedback is about. It's not really about the mechanism down at the center. It's about the conditions that regulate feedback. Okay, and so I'll have to develop this a little bit. So, under what circumstances do you get condensation? There's a long literature on this subject. I think it goes back to Hoyle, 1953. Paul maybe know an earlier paper, but the point is, if you now have a gas blob that's a little denser than the surroundings, you want to go from a single phase to a multi-phase medium. This thing can cool on time scale that's like the cooling time. And it can descend on a time scale that's like the free fall time. And as it goes down, if it can get rid of energy faster than it changes its contrast with its surroundings, then, well, when it descends, as it descends, if it's descending at higher density, it can remain denser than its surroundings, that can continue. Okay. But if it can't, if you cannot lose entropy fast enough to keep your contrast in a medium that's stratified, then you don't create a multi-phase medium. Okay? And this is a visualization of that kind of thing in action, and it follows a number of other similar papers. This was done by my student Greg Neese. And so these are 3 boxes, and this is the cooling time to free fall time ratio in each of the boxes. And when the cooling time is short compared to the free fall time, it just cools in place, and it doesn't, create the structure before it falls. If the cooling time is long compared to the free fall time, you do not develop much contrast up here except for the midplane. But up here, there's not a lot of density contrast developing, because as soon as you descend, you lose contrast. And when the two things are similar in magnitude, you get this lovely lava lamp effect that is fun to watch while you're abusing substances. The point here, though, is it's this ratio that's making a lot of difference in whether or not you can get a multi-phase medium. Okay. Now, there's a paper that Paul's on from 1980 that pointed out that the entropy gradient, the ambient entropy gradient, makes a big difference here. Because if you are descending and the cooling time is longer than free fall time and you have a significant entropy gradient, you will fall through a layer of equivalent entropy, and then your contrast will be a higher entropy blob here. And so this is where you don't develop contrast. The contrast will decrease, and you'll get damped oscillations. Over here, if there's no entropy gradient, as the blob falls, well, it never reaches a layer of equivalent entropy, and it continues to lose entropy, and it can condense. And so in a recent paper, we attached the name buoyancy damping to this phenomenon. And it really makes a difference about whether a medium can condense or not. Now, what can get you around this hurdle? Well, this is a simulation by Lee and Bryan, where this is like a cluster core environment at the center. And there's a black hole, a black hole simulation right in the center. Early in time, the black hole gets fueled by hot gas, but that accretion rate isn't real rapid. When condensation happens, the black hole accretion rate goes up a lot, and what you see happening is an outflow that then induces condensation along the outflow axis. Okay. And I think of this process as similar to a thunderstorm. So in a thunderstorm, an updraft, a convective updraft, pulls humid gas upward. As it goes upward, it expands and cools adiabatically until it hits the dew point. Then you get a condensate that is no longer buoyant, and it falls down. Okay? And so here what's happened, this gas didn't cool out of gas here. This is largely the gas that was lifted out by the outflow. And because it was lifted out, it went to lower temperature. And essentially, you took gas that had a cooling time to free fall time ratio that was several in here. You lifted it out, and let's see, we have this set up. Okay. Well, all right. Then it falls back in, okay? And it is the outflow that caused the precipitation to happen, okay? When you, a bunch of us have stared at the messes you get inside central cluster galaxies for a long time. I think originally people thought maybe this is gas condensing directly out of the intercluster medium. One of the clues that it's not pristine gas is that these regions tend to be dusty, and they go molecular, which implicates some source of dust in, particularly the central galaxy as a source of dust that helps make this condensation process happen. And after watching simulations like the one I showed you, it becomes quite plausible that these things are induced by outflows from the central galaxy. The lifting of gas from the central few kiloparsecs out to distances of 10 or 20 kiloparsecs is what's causing it to condense. These are often oriented along the outflow axis, or sometimes they're just a mess, which is what you get in the simulation after things fall together on the center. And Grant's here, right? Yeah, Grant did some of these. Okay. So why can this happen? This is a simple calculation that, in a way, I presented a more sophisticated calculation at lunch. This is the simplest possible thing you can do when you're trying to figure out how to make an outflow condense. It goes as follows. If you start at radius R1, where your cooling time to free fall time ratio is some number, you can ask, if I now shoot this blob of gas out ballistically, how long is it going to take to come back down? And can it cool before it comes back down? That's what this is meant to ask, or question meant to answer. So if you start out at a certain velocity, let's say it's 1 times the circular velocity, if you start at a cooling time to free fall time ratio of 3, then you can cool before you come back down. That means if you have a medium that has a ratio of a few, it might be stable to condensation if it's absolutely static. But if you just start disturbing the system, if there's radial motions, it causes condensation. And so this is actually volatile, especially if that condensation fuels more feedback and increases the outflow. So systems with too low a ratio of equal to free fall, even if it's several, are quite volatile to being disturbed. As you increase this ratio, the uplift velocity you need to get condensation to happen starts getting higher and higher until it gets implausibly high for any kind of thermally driven uplift process. And you're now in a quiescent state because no amount of uplift is going to help you condense. And that's the reasoning that's draped around the galaxy that you saw. This is the one I was looking for before. The point here is when you do uplift doesn't change the cooling time. What you're doing is you're changing the free fall time. If you start a ratio of 10 down low and go up an order of magnitude in radius, the free fall time is going up an order of magnitude, and the cooling time ratio is now 1. So you're going to cool before you come back down. All right. So here, uplift produces additional fuel. There, uplift gas doesn't condense. And so there's reason to believe that a turbulent circumgalactic medium with a cooling time to free fall time ratio less than 10 can persist. Upshot here, if you're going to quench a galaxy, there's a few conditions that have to be managed. This ratio has to be high enough that the gas isn't volatile. You have to have an entropy gradient, because if you don't have an entropy gradient, buoyancy is not going to help stave off condensation. And you can't have too much uplift, although some helps. Okay. Now, this is kind of the centerpiece. Why do I bother getting up here and claiming these things are characteristics of galaxies? It kind of comes back now to the comparison between a galaxy like NGC 1275 and a galaxy like NGC 4889, the central cluster galaxies tend to divide into two types. Although people, there are many different ways of making that division. Here, I want to divide into things that have evidence for multiphase gas, which could be H alpha nebulosity, and things that have no evidence for multiphase gas. And when you separate those two and plot their cooling time profiles, you get something like this. And there's a bunch of lines in these plots. This brown line is the cooling time profile that you get from cosmological structure formation. You have gas falling together, it shocks, you get an entropy profile, you calculate a cooling time profile, and at large radii, all types of clusters converge to that type of profile. The magenta line is the line you get by saying, let's suppose you have an NFW profile, mass profile, with a single isothermal sphere at the center of it that has a velocity dispersion like a brightest cluster galaxy. And then you calculate the free fall time of that potential, and you put on the magenta line as a function of radius. And so when you graph these things up, if you put enough objects on the plot, what you can see is there's a quite distinct lower limit to the cooling time to free fall time ratio that's right around 10. A lot of things, the upper level of this pink area is 20, and almost everything dips somewhere into this 10 to 20 region. Whereas the things without any multiphase gas hardly go down here. Okay? Almost none of them are down there. And what's really striking about this is, in these systems, whether or not it's star forming has everything to do with the multiphase gas. It is a one-to-one relationship with just a couple of niggling exceptions. And so I think this is saying something important about lots of other galaxies, because this connection is so close. The other thing is, again, this striking floor. When it's hard to see in any one system, but once you plot a bunch of them, there is something quite distinct about this floor in cooling time. So even if everything I told you about buoyancy and suppression in the last 10 minutes is wrong, this is still something that is really calling out for an explanation. So these things, as the AGN heating can't push you very high in cooling time, you're going to cool back down and you're going to be stuck in a cycle. How do you get out of the cycle? Well, one option is conductive heating. And this blue line is the profile. If you just say, if we have conduction that is carrying heat inward, and this is for a 1/3 Spitzer conduction assumption. It could also be, you could get a similar line if you just did turbulent heat diffusion, right? If you raise the cooling time enough at the center, radial heat transport is enough to start pumping energy into the center, and you would go up to this, which is the isothermal profile. Then if you have mergers can happen on gig-year, a few gig-year timescales, you go up higher. So once you get above this line, you can continue to climb. But if you're never above it, you're stuck down here, and the AGN has to be intervening. It also is the case that essentially all the high-power radio AGNs are in this group. So if you wonder, how could the AGN possibly know what the state of the circumgalactic medium is at 10 kiloparsecs, well, the answer is it definitely knows. So after we realized this, we went to look at elliptical galaxies. It turns out there's two kinds of elliptical galaxies. There are some with multiphase gas, like NGC 5044 that Larry David's done a lot of work on. And the things like NGC 4472, where there's virtually none. And this is a sample of 10 objects from Herbert Werner's work, where he has really good high-quality Chandra data and can calculate density and temperature as a function of radius. And the galaxies that have extended multiphase gas, they have a profile that just follows this cooling time to free fall time. It's roughly 10. They end up between 10 and 20, but they go down here, except in the very center. And then the things without multiphase gas tend not to go down in that region, and actually lies a little about it here. With one exception. This is a galaxy that has no multi-phase gas at large radii, but at small radii it does. It's NG 4261. It has a dusty disk down near the center. Its AGN is 100 times more powerful than these others, and it's the only one that goes to a low ratio inside of about 200 parsecs. So one case doesn't prove the rule, but it is curious that if this really is the trigger for AGN, strong AGN feedback, that this thing is showing it. So that's the case for massive ellipticals. Very recently, we tried to figure out how to bring more data to bear on this problem. And the way to do it is to use the following simple quantitative argument. If this is really true, if feedback is just limiting the cooling time to be at least 10 times the free fall time, that ends up being an upper limit on the ambient density as a function of radius. This is just algebra. Okay. And if you have this limit on the density, then you can calculate the X-ray luminosity from within a given radius by 4 pi r squared times the cooling function times density squared. Okay. And the odd thing about that is when you do this integral, you get a luminosity that is inversely dependent on the cooling function, which at first seems counterintuitive. Why, if you put some metals into the gas and make it cool more easily, does the X-ray luminosity go down? And it has to do with this on-size, right? If this is what feedback is doing, and you enrich the gas, then feedback has to push it to a lower density. And then you square density, and the cooling function ends up in the denominator. And you get a nice expression for what the limiting luminosity is a function of radius, temperature is a function in here, velocity dispersion, and radius. Okay. And then you can plot that up. Okay, so on the, here's the, kind of scaling quantity, which is a complex function of temperature, because that's a complex function of temperature. You have X-ray luminosity on this axis. And here you can put on, these are the galaxy clusters I showed you a little while ago. And as you expand the aperture, the X-ray luminosity inside the aperture is getting bigger and bigger and bigger and bigger. The filled circles are 0.04 R500. The filled triangles, the empty triangles are 1.5 R500, just to mark, as you go farther and farther out, what's happening. So at small radii, you're close to this limit for the population that's multi-phase. And as you go to larger radii, you're starting to go more over into the cosmological regime, which deviates. And you can see the single phase ones are not in the precipitation region at small radii. Okay. Next thing you can put on there are Ming Sun's galaxy group cores. And these are just observations within 0.15 R500. And they are also limited by this limit. Then there's this compilation of entropy profiles from Panagulia et al. In 2014, where for objects of around a keV, they showed that the entropy profile goes like r to the 2/3 with a normalization that places it right here. So in this population of galaxies and groups, their entropy profile puts you right about here relative to the precipitation limit. Then there's the ellipticals I showed you. If you go from small radius to larger radius, you tend to go right through this region if you're a multi-phase galaxy. If you're single phase, you're farther out here. To go further than this, what we did is we used a compilation of elliptical galaxies done by Andy Golding. And what the Golding et al. People did is they took the Atlas 3D sample, the massive sample, and used an aperture that corresponded to the effective radius of the optical light. And that was helpful in that sometimes when these studies are done, X-ray astronomers will observe out to the point where the galaxy light, or the X-ray kind of merges with the background. It becomes a background limited aperture. In this compilation, they used an optically determined aperture. And when you lay all those points on, you get that. Okay. So for a much larger sample of ellipticals, you can now push down to much smaller systems, show that this limit still holds, that the trend still holds. And if you ask, how many of these galaxies have CO, if it has CO, it tends to be close to the precipitation limit. Also, if it has nebulosity, which is the cyan symbol, it tends to be close to the limit. Finally, if you put the Milky Way on, this is the Milky Way at 8 kiloparsecs. This is 1 to 100 kiloparsecs. So the Milky Way inside about 10 kiloparsecs is right over here. So over 7 orders of magnitude in extra luminosity, this looks like a very secure upper limit, showing that the physics that's regulating things at this end may be applying all the way down. This is a very steady line, even though this is a complicated function of temperature. So it looks like whatever feedback does simplifies to this threshold. It's putting an upper limit on the density that is determined by the tendency to go multi-phase. Okay. Here's another way of looking at the same data, and it gets to the LXT relation for clusters and downscale. So now what the plot's doing is it's saying it's well known that if all objects had cosmological profiles, they would adhere to this purple line. This model is a model where you're essentially taking the cosmological profile. Yes, feedback suppresses you here. You're taking the cosmological profile and saying at some radius it becomes limited by this limit. Okay. In a galaxy cluster, R500 is like a megaparsec, and this is like 30 kiloparsecs. Whoops, went the wrong way. In a galaxy group, this is like 500 kiloparsecs, and that's 100 kiloparsecs. When you get down to galaxy scales, they're like the same. The whole CGM out to R500 would really be in the precipitation limit if you have a massive galaxy.
Can I ask a question?
Sure.
So I know this isn't the case, but you have luminosity on one axis and energy on the other.
Right.
And this is not trivial because you're saying that if the self-similar line, or why is this not just a trivial?
Okay. If all these objects have the same structure, same density structure, okay, just scaled up.
Then it would be that blue line.
Then you'd be up here.
Okay.
And in fact, your orders of magnitude below it. Okay. Yeah. So this is what galaxy clusters do. Galaxy clusters in groups. And you can fit them and extend the line down here. And so this has been known for a long time that the luminosity temperature relation is steeper for galaxy clusters in groups than the self-similar prediction. The new thing is studies that, this Anderson et al. Study. What they did is they took the Sloan Digital Sky Survey, they took 250,000 galaxies, luminous red galaxies, binned them by stellar mass, and took Gross et al. Sky Survey cutouts and stacked them. Okay. So the idea is in any one of these galaxies, you can't really observe the circumgalactic gas around it. But if you use cutouts that have a radius R500, you can stack a bunch up and see how much flux there is, typically in that bin. And yeah, the fact that they agree up here is trivial. It's the same kind of stuff. But as you go down in mass, you can go well beyond the individual objects you can observe on group scales. And the relation has the same slope and the same normalization. So you cannot, right, these objects, you might be able to observe them directly out to 10 kiloparsecs or so. But it looks like there is indeed more gas out there that follows this relation out to R500. Similar things have been done with Planck stacks. Okay. And if you put the Milky Way on this plot, if you go out to 100 kiloparsecs, it's kind of remarkable that you take the luminosity temperature relation for galaxy clusters and extrapolate it down the Milky Way, it still works. Yeah.
So presumably, galaxies, when they first form, they form on this self-similar perhaps, and then they have a very transient phase during which they adjust. So there could be some transient phase. I mean, what you're describing is the steady state that
right.
is long-lived, but there could be an early phase where...
Yes. And I think that, so I will return to that because I think that's absolutely right, and it gets, yeah. what I calculated here is the steady state the galaxies are trying to achieve. And the things that prevent that are mergers and filaments and whatever. They're short-lived, trying to keep you away from here. I don't think you're ever up here because this would mean everywhere the cooling time is way less than the free fall time. So you will go. The point about this is you will go and condense out if you get too high in this direction. But you might have a tumultuous mess. It's more X-ray luminosity. But getting up here, you can't ever get there because you'll just condense out. You just can't reach it. Okay. All right. So yeah, the idea that feedback, whatever it does, enforces this seems to be borne out by the data. And in a way, if this really holds, it is a comfort to people who are worried about how chaotic AGN feedback looks. Because it turns out maybe the mechanism isn't so important as the emergent behavior that it produces. Right. And so this can be simulated. One of the first, I think concurrently, Max Guthrie is going to give a talk at like 4:30 on this very subject. This is one of his early simulations where it is bipolar outflows that are fueled by condensation, and clearly it self-regulates. Okay, and this had a big impact on my thinking, seeing this, and he's followed up with a bunch of really good papers that don't have time to discuss, but if you run over there at 4:30, the Einstein Fellow Symposium, maybe he'll talk about it. This is a simulation by Yuan Li, where now you're seeing a bigger view, 300 kiloparsec view. And here it goes. It is fueled by condensation. And now there's star formation put in. So this fuel that you've made eventually goes away. And when it goes away, the process starts over. Okay. So this simulation is cycling a bit between making cold gas. Cold gas fuels the AGN. When the cold gas goes away, condensation has to make more fuel. And you can see the waves it's creating and all that around the galaxy. So if you just look in this simulation at the mass of cold gas and then in T=T free fall ratio, what you find is when it gets low, you get cold gas, and the system now regulates in a ratio of 10. When the cold gas goes away, the T-cool drops, you trigger cold gas again, it goes up here. And so this is self-regulation in action. There's coupling between the condensation behavior and the state of the medium around it. Now what I want to show is the entropy distribution of this simulation in detail, because these principles of buoyancy and convection and instability are very nicely illustrated in this set of movie clips. So this is that same simulation you saw, which starts in a state where it's homogeneous at each radius. And here is the T-cool 10 line at a time of 0.27 gigayears. And right here, the cooling time is about 0.2 gigayears. And we'll watch the movie, we'll advance it 100 gigayears, and you see condensation happening way out here. That's not gas that condensed down this way. This is gas that got lifted out. Okay. So what you see here is the leading edge of the bipolar outflow at high entropy. And down here, uplifted gas that can now condense. Okay, and at that moment, very early into this process, you have a power law entropy distribution going down towards the center. In time, it flattens out near the center. And when it flattens out, you can no longer suppress condensation through buoyancy down here. Okay? And out here, you see stuff that looks like it's going to condense, but if you watch, it's not going to because of the buoyancy effect. It'll just sink down to a layer of equivalent entropy faster than it can condense, and then it doesn't condense. Okay? Now, the AGN has shut off. You see this is flat in here, and it breaks, and the break point is right about T4, T 10. If we let it go, you will see damping happen here. You will see condensation begin right where this flattens. Okay, here it goes. That's where it goes towards condensation. Condensation is suppressed where you have an entropy gradient. It's not suppressed where it's flat. And boom, same thing happens. Okay, and point being that if you want to know whether a CGM is multi-phase, whether a galaxy can be quenched, regulation of the entropy gradient slope is an important feature because it makes a lot of difference when it comes to condensation. And we do it again. Well, and I'll keep advancing. Next thing. Okay. Does this work with all kinds of feedback? My thesis student, Greg Meese, who's now a data scientist in the medical industry, prepared this set of simulations for his thesis. And this is similar to one you saw just a few minutes ago, but now the ratio of kinetic to thermal feedback is being manipulated here. And if I let them go, you'll see one is different from the others. When some fraction of feedback is kinetic, you get a self-regulating system. But if it's all thermally injected feedback at the center, it doesn't self-regulate. Okay? And it's not primarily because the feedback's kinetic. It has to do with the radial distribution of energy input. When you have purely thermal energy input at the center, you are raising the entropy at the center and causing convection. When you cause convection, you flatten the entropy gradient. When you flatten the entropy gradient, condensation can happen everywhere, and you cannot get out of that state unless you overheat the center. That's the only way out. If you have a bipolar outflow, you can distribute heat farther out in a way that maintains the entropy gradient so it doesn't condense out here. All you need to do is regulate the center because condensation is damped as long as you don't invert the entropy gradient. A very large proportion of AGN feedback simulations to date have done this. You can't get that to work, period, because of physics. It has nothing to do with simulation method. It has nothing to do with whatever mechanism you tune up. It has to do with the physics of buoyancy. Yes, Bob. Oh, hi. Hi, how you doing?
Only 10% of AGNs do have outflow. I mean, jets.
Jets.
So maybe it is the outflows that are broader than the jet that you're referring to.
I'd say the key here is for feedback to be asymmetric. I know in illustrious TNG, they accomplished this by shooting bullets. the Yosemite Sam version of feedback, you're shooting bullets all directions. The idea is when you do that, you are focusing your energy into a momentum flux that carries it out and dissipates energy at large radius. If that happens, you can put the heat out here and regulate this while maintaining the entropy gradient, which is the key to stopping condensation, or at least to limiting condensation. And I think this is a very deep statement about AGN feedback. Yeah. When Lustrous did this, by the simple switch of going from a thermal type to just kinetic bullets, they went from galaxies that did not have a red sequence to galaxies that did have a red sequence. And I think it's basically this effect. It can become self-regulating in a way that the pure thermal can't. Yeah. I only have a few more minutes left. I wanted to say a few words about implications of galaxy evolution because it does get to the point that Avi was making earlier. There's a giant industry that thinks of feedback as a wind-regulated mechanism where you have accretion coming in, and if a large fraction of it gets into the galaxy, you have to blow a large fraction of it out in order to get correct baryon fraction. And that gets even more critical as you go down to smaller galaxies. Okay? Usually people think of there being a wind that goes out, and often the mental picture is once the wind goes out, you don't have to worry about it anymore. It's like gone. Right? There might be some recycling. But in this kind of a system, the regulation principle is internal to the galaxy. Somehow you have to have that mass loading factor be just right in order for this to produce galaxies like Earth. And maybe this is what happens early in time when you're not regulated. If instead the branching is the opposite way, if you have branching where most of the gas that is accreted ends up in the CGM with only a smaller amount coming in, you can kick out only about, you don't need a big mass loading factor. What you're really relying on is recycling to keep populating the galaxy with gas. If that's the case, then the regulating principle is actually the condensation rate. And if you don't have a strong wind, what you're doing is you're heating the circumgalactic medium. It's like a balloon, right? You're expanding it. You're driving it on lower density if it has to go lower density. But if the feedback principle is I have to push the density down until I don't condense, your expandancy is going to get stuck here. And I think this is the state of Galaxy is trying to get to. Early on, it probably does something like this. And I think what's interesting is to figure out when this transition happens as a function of halo mass. Because I think large halos at late times are quite credibly doing this. What I don't know is how far down that principle still applies. Yeah. There's some fun papers about this. I'm not going to try to explain abundance saturation because you're about to do this, like I'm number one. But first it's high and I'm number one. The point is, through that precipitation type regulation mechanism, you can reproduce quite naturally the mass velocity relation, the Baryon fraction as a function of halo mass, and the M sigma relation too. I'm not going to go into that. If you read the paper, it's like a 4-page paper that derives all that from precipitation principle. It's either an amazing coincidence or it does have something important to say. Yeah. And yeah. Last statement I wanted to make is just that the real tests are in the circumgalactic medium. And what's really interesting is dynamics. I want to end with this slide. This is from Xiao and Chen's group in Chicago. And what she did is she looked at thousands of Sloan galaxy lines, or quasar lines of sight for magnesium 2 absorption lines that went close to massive galaxies. And found a bunch of them. And around a population of massive galaxies where the central velocity dispersion is like 300 kilometers per second, the velocity dispersion of the CGM clouds is half that. Okay? If you had ballistic infall or outflows that were destined to leave the halo, you'd expect a much higher velocity than that. But in fact, you see a velocity that's only half the stellar velocity dispersion, which implies they're suspended in something else. I'll stop there.
So when you look at the M sigma, that's a very interesting result. Overall, the picture that you described makes a lot of sense. One of the puzzles about black holes in the most massive galaxies is that there is a cap. It's about 10 to the 10 solar masses on the black hole mass. Can you derive an upper limit, or is it like, would you expect things to continue to grow as structure builds? Why do clusters have the biggest black holes the same as the high range of quasars? That's
okay. So the way this comes about, right, this is basically the scaling issue. What it's saying is, here we're saying, what's the black hole mass that corresponds to the black hole's energy production compensating for the luminosity of the CGM over Hubble time? Okay, and you get this result. This is actually the luminosity of the CGM in the region that needs to be compensated. Okay, when you do this calculation, what happens is you get, instead of sigma v to the 5th, you get sigma v cubed times temperature. Because the temperature comes in, you're trying to replace the luminosity. Okay? And so when you make that correction, you say, we're not going to use sigma v to the 5th. We're going to use sigma v cubed times temperature. Your brightest cluster galaxies go to here. Now, if you use temperature to the 2/5 or 2.5, they'd be way over here. But instead, they're here. So if you're looking at M sigma in particular, because black holes, or since central galaxies don't have a larger velocity dispersion, you have this picture that goes this way. If you make this argument, the correction goes to here. and it puts them right on the line.
And that's true at high redshifts.
I don't know about high redshifts.
The interesting thing is to compare quasars, which are in smaller objects, smaller halos than clusters.
Right.
You have the same cap on the black hole mass, and it would be interesting to see.
Interesting. Thanks for bringing that to my attention. While this is up, I also mentioned that when I made this diagram, I had no idea there was a controversy over pseudo-bulges. Right? The vanilla version of this model predicts a steeper M-sigma relation in smaller halos that goes through the solar bulges. You know, I'm not willing to go on a big limb about that, but it's curious that it predicts a steeper relation down here.
So your evidence, observational evidence, is kind of statistical. So you've got a bunch of galaxies and a correlation, and you, as you said at the beginning, you're not going to talk about how the gas gets into the center.
Yes.
But is there some way to investigate the question of whether the center of our galaxy is in the quiescent state of the precipitation-regulated feedback, nonetheless?
Okay. I guess I have a few comments on that, I guess. One is, if you're interested in how gas gets down to small radii, again, Max Gasperi has run some really beautiful papers about that, and physically interesting. The point is, for this mechanism, how does it overcome the rotational barrier, right, and the air momentum problem? The way it gets around that is if you have enough turbulence, okay, and you're constantly condensing out, you're always populating a low angular momentum region of phase space. Okay, so those things tend to sink in, and if you're constantly populating it, you're always feeding stuff down towards the center. And he's followed this effect down to about 40 gravitational radii. And if you have a turbulent velocity dispersion that's greater than the rotational speed, then this mechanism transports cold gas in toward the center by this, you can either consider it, clouds running into each other and canceling the angular momentum, or just condensing on, in a low angular momentum region of phase space. And so I think that's cool. It's kind of saying, here's a way, if you get this instability to go, of actually getting condensed gas close to the black hole in a way that gets around the angular momentum issue. And it relies on there being turbulence in the hot medium, and then you condense the gas out. So that's interesting. Your second question was the Milky Way. When I think of the Milky Way, this is now speculation. I think there's reason to believe the Milky Way has a short duty cycle in the energetic phase and a long one out of it, right? If you set off a burst of energy in a lower mass halo, you can send the gas to quite a bit longer cooling time than in a galaxy cluster. So, this falls to carry punches. When I see the Fermi bubbles, I think I'm looking at an event that happened a few million years in the past, but it was brief because it shut itself off pretty quickly. But it may well happen again. That's what I think. I can't prove it now. That's how I respond to a question like that.
Other questions? If not, let's thank our people.
Mark, that was beautiful. How do you exercise these things together?
Well, I think so.
It's beautiful. It's beautiful.